Okay, so I'm going to start out this video once again with Chuck Penson's excellent book, Heathkit Test Equipment Products. I'm going to flip to the Analog VOMs, Multimeters, and Voltmeters chapter. And I've already done several other meters. I've done a video on the IM-17 and its bigger brother, the IM-25. Those are two meters that came out the same time in 1967 and have essentially the same design philosophy. It's a little weird, it does work, but it's not very great. I think they were more conceptually useful than practically useful, but yet they were made for a number of years. Now, there's another meter in what's really the same design philosophy family, but it's a portable meter, and that's the IM-17. Also came out in 1967 and was made a little bit later. It made it up to the 1977 time frame. And Heathkit temporarily discontinued it after 1977. But then, let's see if I can find it here. Yeah, in 1979, so after a hiatus of a couple of years, they brought it back as the IM-5217. The only real difference being the style of the knob and the color of the paint on the sheet metal part and the color of the blow molded plastic case, which went from brown to blue, so it had the later color scheme, but otherwise it's exactly the same. Well, I'll take that back. It did delete one thing. The IM-17, both versions of it, and I'll get to that in a minute, had a 1/4 inch phone jack, either located up here below the knob or around on the front, depending on the version. They just relocated the jack, and that was for an auxiliary test probe. They must have determined that people weren't really buying those, and they could save a few shekels by just not having that jack on the 5217. Otherwise, it's the same exact design. So going back to the IM-17, it had two versions. It had originally a black plastic injection molded case, which wasn't that great. It didn't look very good. It I think was very fragile. The plastic is kind of thin and doesn't take much of a beating before it cracks. And then they replaced it with a sleeker and ultimately more rugged blow molded case of a different type of plastic. I'm not sure what type. That was in a brown color, and there was a whole series of primarily automotive test equipment that Heathkit had around that time, which used the same case and the same, I think the same meter movement with just different scales on it, and you know, they would look very similar. Now, Chuck's book says that the streamlined version originally came out in black, sort of like the other earlier case, but then changed to brown. I've never seen one of those, but that's what it says here. The circuit design on here, like I said, is so similar that it's pretty clear that Heathkit designed a family of voltmeters from the fairly deluxe IM-25 down to the somewhat stripped down IM-16, which primarily left off the ability to measure current. It just went down to voltage and resistance, very much like a VTVM. And then with the IM-17, they kept that limitation and then reduced accuracy, had fewer ranges, a simpler scale, reduced accuracy, but it still measured AC and DC volts and resistance. So this video is going to be about the IM-17. Alright, here's the inside of the IM-17. This one's been modified by a previous owner to use a 9-volt battery in place of the 8.4 or whatever it is mercury cell, or battery, I guess technically. I'm not sure if it's a battery or a cell. That would be in here in a totally different kind of holder. The old holder has been removed, and this snap-in type of 9-volt battery holder has been put in there. I'm not too keen on it because it comes right up against the back of the meter here, and you have to discombobulate the entire thing in order to replace this battery. You can't just slip it out with it in its current position, so I don't care for that too much. Now, one thing the previous owner has done is they put a diode, I don't know what kind of diode, and another one there on both the plus and minus leads going into the original holes, obviously to try to get some voltage drop from the 9 volts down to something else. I don't know what type of, if those are germanium diodes, maybe that would be an appropriate voltage drop. I know from working on another one of these that it also works just fine just using the 9-volt battery without the diodes. But I'm inclined to leave these in here. The only thing that I wonder about is I don't like this battery holder. And I'm not sure what I might put in there instead of it. Anyway, so you've got the meter movement here, and it helps support the left side of the board. These nuts are rolled up to the proper depth, and then washers are put on. Then it goes through the holes in the board, and then star washers go on, and then another set of nuts, and they clamp the circuit board onto the 2 meter posts, and that holds it. And then on the other side, the big selector switch here goes through and holds the right side of the board. Now, so far I have replaced 2 out of the 3 test leads because they were in pretty awful shape. They were pretty good quality test leads, but they were rubber, and the rubber had hardened, and I put in some new Pomona silicone rubber test leads of the same length as the original. The gray lead is actually a shielded cable, and I was able to clean that up with isopropyl alcohol. And I put on the original alligator and alligator clip and red test probe onto the leads in the method recommended in the manual. So those are taken care of. Now I have a black case for this and a brown case. The IM-17 originally came out with a black plastic case that any ones you find today tend to be badly cracked and falling apart. And I don't much care for that style of case. They, I think, fairly quickly revised the IM-17 to use the same brown blow-molded case that they had used on lots of other meters, including a whole bunch of ones intended for automotive work. And unfortunately, the ones of those you get today tend to have broken latches and broken hinges, so there's almost no winning. I was looking through a whole bunch of eBay listings on these, and they either had broken black cases or broken brown cases. So I figured I like the brown case better. I'm going to see how I can rig it up to work. And the sheet metal is identical between the black case and the brown case models, except that the graphics here and here are different. This here is the guts of a black case IM-17, and the way that one hinged open, this jack here for an auxiliary test probe could be on the front inconspicuously, and in red lettering here it says utility solid state voltmeter, and then the model number IM-17, and nothing up here. But on the brown case model, because the bottom half of the case comes up more or less level with this, you could not get the 1/4-inch phone plug from an auxiliary probe in here so they relocated it up to this position, and then the solid-state voltmeter part got relocated up to here, graphically speaking. And actually it didn't say utility solid-state voltmeter. I think it just said voltmeter, actually. I think it was big letters that went almost all the way across here that said voltmeter, and left off all that other text such as utility solid state. And then the Heathkit IM-17 text was moved way down here to the bottom below the jack. So this is the one I have, and I've already test fit it into the brown case I have, which was from a trashed IM-17. So I'm pulling the guts out of a black IM-17 and putting in the case for a brown IM-17. I'm not going to be able to do anything about this jack. I could drill a new hole, but then it would trash the graphics. I'm never going to use this jack, so it might as well be in a position where nothing can be plugged into it. And the graphics here, the silk screen is in very good condition. So I think I'm going to shoot this thing with a little bit of deoxit. It probably doesn't need it, but I'm going to do it anyway. Oh, then let's look at the rest of what's in here. So it has the original battery holder for a C cell, and that provides the I believe that provides the excitation for the ohms function. And then, well, yeah, I think that provides the excitation for the ohms function, and probably also the power supply for the meter driver circuit. I'll have to check that in the schematic. And because this one was a mercury cell, I'm inclined to think that that was one that's being used for the reference voltage for the constant current source for the ohms function. And actually, the more I think about it, I'm thinking this guy probably provides the excitation for the ohms function as well. And this one's probably just providing the voltage for the meter drive, but I'll double check that. I could be guessing wrong. I have not looked at the schematic yet. Over here we've got 3 transistors, and over there is, in the metal can, is an FET, and over there is another transistor. I think we'll find that at least those two are probably part of the high impedance front end circuit, and then these guys here are probably part of the differential drivers for the meters, and I'll figure out what Q3 does when I look at the schematic. Otherwise, when we look around the other side of this, we've got the 2 front panel, Heathkit called them controls, probably figured that the average customer couldn't figure out what potentiometer meant. And this one is for zeroing the meter electronically, and this one is for setting the full scale in ohms mode. And then you've got the 2 switches. They're all wired out with twisted pigtails to the circuit board. We've got the master function switch here. All those resistors are part of the resistor divider for the voltage function, and they probably also factor into the ohms function as well. Down there at the bottom we have a couple of trim pots, and those are used for the DC cal and what's the other one? The AC cal and DC cal. And then here we have a couple of capacitors, which are almost certainly part of the AC voltmeter DC blocking or AC coupling, depending how you look at it, function. I don't know what else they would be doing. There doesn't seem to be anything in the way of electrolytic capacitors in this one. To address an issue that I brought up earlier, the 1.5 volt cell on this meter is being used as the entire circuit, both the excitation and the precision current reference for the ohms function. So that's all taking care of the ohms. The mercury cell that was in here, 8.4 volts, that was used on the IM-17 and the IM-25 as a reference voltage for the constant current source for the ohms function, where it was really important to have it be a reliable voltage. But on this meter, the mercury cell that would normally be here is being used only to power the meter circuit. In other words, the circuit that actually swings the meter movement, the amplifier for that, which is after the measurement stage. And the voltage is not critical. It gets dialed out pretty easily with the other controls. So, you know, I don't know, it's kind of odd that, well, it's not odd that the previous owner of this meter decided to use a 9-volt cell in place of the 8.4 because it's close. And then he put 2 diodes in series, as I mentioned before, one on the plus side, one on the minus side. And I checked the part number, and it's not in the 4000 series, but it's still a general purpose silicon diode with a nominal forward voltage drop of 1.4 volts. So that's 2.8 volts of drop off of a 9-volt battery. So, you know, 6.2 volts. 6.2 volts is what's actually being applied to the meter circuit when it's expecting 8.2. I have no idea why the guy thought it was a good idea to use 2 diodes there. I could see dropping it a little bit and throwing in maybe a germanium diode, but I don't know. It seems to work. I don't see any other components he changed, so it's a sloppy circuit. It's able to work with quite a wide range of voltages, apparently. Okay, let's do a demo. I've just completed the calibration process per the Heathkit manual. And first off, I need to zero out the meter, so I take the zero control here and adjust it until it's right on 0. And I'm in the DC volts lowest range, so 1 volt would be full scale, 1 volt would be up here, and I've got the DC plus and minus switch in the plus position. Alright, with the power supply set to 0.1 volt but turned off, I'm going to turn the power supply on, and it goes up to about the 1 position where 10 is 1 volt, so it's showing 0.1 volt. And 0.3 volts, it's pretty much right on. 0.7 volts, pretty close. 1 volt, pretty much full scale, slightly over. Now if I go up to the 10 volt range, it should be sitting around 1 volt. And at this point I'm going to go up in 1 volt increments. 2, 3, 4, 5. Whoops, I bumped up to 6. There's 5. 6, 7, 8, 9, 10. And then I'll go up to the 100 volt range. And once again it's sitting around the 1, which is 10 on this scale. And I'll go up to 17 volts. It's about right where it is. To 20 volts. Just on the high side of the mark. Let's go up to 30 volts. Pretty much right on. My power supply peaks out at 32, and that's right what it's showing us. So DC volts is working fine. And I should mention that for this, I'm using the black alligator clip to the negative of my power supply, and the black test probe on the meter to the positive side of the power supply. This is the probe that has a 1 mega ohm resistor inside of it. It also has a shielded cable, even though it looks like just a gray insulated wire. It's actually a shielded cable, but the shield is not terminated at this end. There's nowhere to terminate it to. The DC volts function is the only instance on this meter where the black probe gets used. Otherwise the red probe gets used for everything. Okay, for AC volts, I'm going to go up to the 100 volt range. And I'm going to make sure the meter is zeroed, since I just changed functions. It's a different circuit driving the meter circuit, so I make sure that's zeroed out. There we go. I have the red lead and the black, or the alligator clip, connected to my AC power access panel, which I have a YouTube video on, and that's plugged into my Variac. Make sure it's turned off. I'm going to go up to the 140 volt position. And I'll start cranking it up. Oops, I have to turn this switch on too. Okay, so somewhere around 50 volts. And I should be using the black scale. This is color coded. Use the red scales when it's indicated here, and the black scale on the meter when it's indicated. So I should be using this black scale. It's reading a little high. The meter on the Variac's also reading a little high. Yeah, that's more like it. 50 volts. And if I go to around about 100 volts, it's slightly over range there. The Variac meter is not very precise. And if I want to read higher, I can go up to the 1000 volt range, and it's reading about 100 on the 1000 volt range. So if I go up to about 120 volts ish, well, it's reading low here because again the Variac's not very accurate. That's more like it. Anyway, so the AC volts function is working. Okay, this meter does not test amps or milliamps at all. All it tests is AC and DC volts and resistance. So I'll go straight to the resistance, and I'll set it for the ×1 multiplier. And let's see, it's reading something on the order of 1 on the meter when it's connected to a short here at the decade resistance box. And I think that's because I have roughly 1 ohm quiescent resistance in the test leads. So it's almost always off by about 1 ohm. So I think we're okay on that. Now let me connect it over here. Got a bad connection. You can just see it's kind of iffy. Not making good connection. Anyway, so let's just go with that. I'll put it up to about 5 ohms, and it's definitely reading low. But again, there is no calibration. Actually, let's check that out. Maybe let's make sure the meter is set up properly. So with the leads shorted out, well, come on. I should dial it down to 0 here. And with the leads open, I should be getting infinity, and I'm not. So I adjust the ohms pot on the front until I get infinity. I go back and forth and double check it at the other end, and it's still reading 0. So now I should be getting about 5 ohms, and it'll be on the green scale. And this is color coded. The ranges here are in green ink. Well, it's reading about 4 something on there. This kind of meter is notoriously inaccurate when it comes to resistance measurements. Let's try giving it something a little more substantial. Let's give it 20 ohms. Well, it's reading a little low there, but I've changed, let's see, make sure I've got good connection. Yeah, it's just reading a little on the low side. 30, still reading on the low side. About 60, definitely reading low. Let's double check my 0. Infinity is still infinity. 0 is reading low. It's drifted, so let's try bringing that up. Check infinity again. Now it's reading high. Bring that back. Recheck low. And now let's reconnect it up here. It's reading about 50 when it should be reading 60, but again, there's no adjustment on this for that. You just have to go with it. It's resistor tolerances and so on inside the meter. Can't do much about it without replacing everything. And even then, the specifications are so poor that all you're trying to do is get in the ballpark with this. You can't really hope for better. So let's go up to 200 ohms, and I'm getting up really high on the meter here, so I'll go to the next scale, which is the times 100 scale. And now I'll take whatever the reading is times 100, so it's right on 2, so that's 200, and that's exactly what I've got here. It's starting to read a little better. Let's go to 600, and it's right on. 800, pretty much right on. Let's try bringing up 4K. Well, it's reading halfway between 30 and 50 times 100, so yeah, it's reading 4K. So that's reading pretty well, but now I can go up perhaps to the 10K range and see what I get there. Well, it's very low, but it's on the low side of halfway between 0 and 1, so it's not doing too badly. Let's try bringing up 30K, and we're on 3 times 10K, so 30K. Let's go to 80, and it's right on. Let's try giving it 700K. It's kind of in about the right place you'd expect it to be there, but I can also go to the 1 meg range. And there it's reading, you know, it's reading a little on the high side of 6. So again, within the limitations of this meter, the circuitry that's used, the nonlinear scale on the meter, it's doing a pretty good job. It's basically working within the accuracy that Heathkit specified. It definitely is doing that. So here's the brown case I have, which is the second version of the case offered on this kit. The original one was a hard molded plastic case in a color of black. The brown ones came later and are blow molded instead of injection molded, which is what I think the black one is. This one isn't in bad condition overall, except for the fact that the same thing that happens to all of these has happened to this one, namely the very thin parts that make up hinges have crumbled, and there's just no way to resurrect those that I'm aware of, so I have to come up with something to at least make this functional. And this is what the other side looks like. Now the latch that goes over this is also broken off at its hinge, so I'm going to have to cut that off and do something different with it. And I think probably what I'll end up doing with the lid is just remove the vestiges of the plastic hinge and glue on some sort of a cloth hinge. Try to do as neatly as possible. The original label, which went here on this particular case, was all wrinkled and damaged. I peeled it off and used adhesive remover to remove the dried adhesive behind it, and I was lucky enough to find a brand new label for this model on eBay. I don't know how somebody ended up with one, but I do have a brand new label to go here. So it's really just a matter of fixing the latch somehow, something to make the case stay shut basically, and then replace the hinge. Another thing with these cases is that the outer shells are actually quite thin, and I found a couple of areas like here where there's a crack, and down here where there's a crack. I don't think there's any on the top half. You have to keep in mind that these entire things were blow molded as one big assembly. Okay, a little two-part epoxy smeared around there, and just similarly on the other place back down around there. That should stabilize that, although the plastic in general is brittle enough where it'll probably crack somewhere else. And meanwhile, I've prepared a length of 1-inch wide nylon web strapping or belt, just from the hardware store. I've cut it and fused the ends so they won't unravel, and I think this will work. I just have to think through the different types of adhesive I have and which one will work best. I'll probably end up using epoxy, but I'm not sure how well it'll hold. I gotta scratch my head a little bit on that yet. I've decided after some research to give this product a try. The Loctite vinyl, fabric, and plastic flexible adhesive for rubber, leather, wood, metal, glass, ceramic, men's rips and tears, waterproof, 30 minutes, flexible adhesive, transparent. Adhesive is highly flexible to withstand bending and torsion. Used on seats, upholstery, rainwear, camping gear, wading pools, fabrics, and plastics. Okay, I've roughed up this lip here with some sandpaper. Per the instructions, I figure the nylon web belt is rough enough by itself. I've got some masking tape to help hold it in position while the glue dries. And I have a piece of wood and a couple of beam clamps to clamp it down and put some pressure clamping it between the wood and the edge of the table saw table. Well, the wood clamp bit didn't work because this piece is tapered down and it keeps wanting to flip off of it. So instead I've got the tape adhering to the case and pushed down hard against the edge, and I think I've worked the adhesive into the webbing enough where it'll have a chance of holding. We'll see. Well, that stuff didn't work at all. After it dried, it just peeled right off. I'm not sure what the problem was, but it definitely did not hold at all. I think I'm going to go back to the epoxy and just hope that works. Alright, the next day I've got the fabric folded over the edge and epoxied. I have so that the seeping glue won't get stuck to the wood. I've got the wood wrapped in wax paper. I've got the wood held up by masking tape so it won't fall down. And then I've got my semi-heavy portable shop vac pushing up against the wood so that it doesn't stray this way, and then the whole thing's up against the fence of my table saw, and it's pushed up there enough to keep the fabric against the plastic while the epoxy sets. I was worried that some of the epoxy from up here would have wicked into the fabric and prevented it from folding, but I think a little bit did right along the edge, but it still goes around the corner. We'll see. Alright, it doesn't look too horrible. I did spill a little epoxy there that I should have cleaned up, but alright. I mean, it looks okay. Let's see if the lid opens right. That's the key. Seems to work. It opens very freely. I don't know how much abuse it'll take before the epoxy lets loose of the plastic. That's my concern with that. Matter of fact, I'm thinking that, I don't know. I guess there's enough. I was kind of alarmed to see there didn't seem to be much epoxy right along here, but it's in there a little further. I think it's probably good enough. So, we've got a workable hinge. Let's see what we can do about the lack of a latch here. I still want to keep this lip because that's what I'll grab to lift it up. I have to figure out if this area here lines up with this area here where the hole is. Alright, I used a 1/4 inch Forstner bit to drill 2 holes here and 2 blind holes here. This is a thick piece of plastic here, so I couldn't actually drill through it without going through the other side. Here it's fairly thin. I'll probably need to put some sort of a backing material up under here, as it turns out. I'm not sure what I'll use there. I might just use a piece of wood to cut to the right size and just push it up under this lip and glue it into place. It's probably the easiest. I have these little 1/4 inch diameter neodymium magnets, and the depth I have these holes cut to will allow one to sit in there and be fairly flush. The other ones here, it'll go through a little bit. So I suspect what I'm going to have to do is put a backing piece in there and then recess these a little bit more with the Forstner bit, just to have something for the magnets to sit on. I don't think I can get them in there just grabbing the edges of the plastic here. Okay, I cut this little piece of pine scrap, and if I slip it up under there, see if I can find the reference marks I made. Yeah. So that will fit up in there. Feels like it's a pretty good fit. I just took the measurement from the outside here and the outside here, and the thickness of the plastic as I measured it here, and then subtracted twice that from the outer dimension and figured that's about what the inner clearance was inside, and it cut the wood and it seems to be just about right the way it was done. So I'm going to put some epoxy on this and stick it in there. Alright, that worked out pretty well. The epoxy is mostly dried, and I put the Forstner bit into it just enough to make an appropriate recess for one magnet. So now I'll just glue the magnets in. Okay, the magnets are epoxied into the holes. These came out really good, sitting on that wooden piece underneath. The holes up here were less evenly done. This one worked out pretty well. This one, the hole was a little too deep, and I didn't realize it. It seemed like it was the right depth until it started sinking into the epoxy, and I couldn't get it back up again without making a real mess of it. It's only slightly shallow, it'll still work. So I just left that alone. Once that cures, I think this case will be ready to put the meter back into. Alright, I didn't like the way this looked. Every one of them is at a slightly different angle and depth. So I kind of sanded over the top of them. And then I've got a thick layer of epoxy across the top. And then I'll sand that down level. And I might even put some paint on it for cosmetic reasons. Alright, after the epoxy hardened, I sanded it level. Same thing over here. And now I'm just going to touch it up. I've got two different paints that might be about right. I've got the Italian dark brown, which is kind of similar, and the military brown, which is also similar. Alright, let's see how that works out once the paint dries and it becomes less glossy. Well, the paint dried. It's definitely not the same shade. And it's, I thought it would be a semi-gloss, but it's flat, which doesn't match the smoothness of the plastic. Well, I'm after functionality here. Anyway, I mean, it came out looking okay. And with those magnets in there, it holds it, but not super strong. I'm not sure it can even really hold it against its own weight, which is disappointing. If you carry it around this way, it'll hold it. But if you tip it upside down, it'll barely hold it. I can't really get any stronger magnets in there. Anyway, I think that's about as far as I'm going to be able to restore this case to functionality. I got to put the label on here yet. Okay, I'm going to put my replacement label on the case. There we go. And it popped into the case pretty as you please. As I mentioned before, this particular version of the meter chassis not being from the same version level as the case, the jack for the auxiliary probes is pointing out the wrong direction to actually get a plug in there. But this is the one I have, and this is the case I have, so they're going to have to go together. There's the beauty shot. So let's take a look at the manual for the IM-17. This one's got some water damage, but it's still intact, which is good. And whoever built this thing, built the kit that came with this particular manual, and the manual did not come from the same place as the meter. Those were different eBay purchases. They used a very bold pencil. I'm not sure about that, because you can hardly write with a pencil that bold. That's the kind of pencil you use if you're doing woodwork or something. Anyway, so you start out with the usual schematic symbols chart, very antiquated one. Your table of contents, photo of the complete meter. Introduction. The Heathkit model IM-17 utility solid-state voltmeter is a compact battery-powered voltometer. And they just kind of ran it together, voltometer. It is accurate and easy to operate. Well, I disagree about the accurate part, but reasonably accurate for a utility meter, I guess. The copolymer case, and I'm not sure, well, I can tell from the photo that they're referring to the later case, the streamlined case, so that's a copolymer case, whatever that means. With probe storage compartment makes the meter especially suitable for service calls as a portable instrument for use in the field and for general utility use. Its simplicity makes it an ideal construction project for the novice in electronics. The high input resistance of the voltmeter on DC voltage ranges places very little loading on a circuit being tested. The 12-position selector switch provides 4 separate ranges, each for DC voltage, AC voltage, and resistance measurements. A DC polarity switch allows upscale readings for either positive or negative voltages without the need of reversing the test leads. The large 4.5-inch meter has 4 easy-to-read scales. An accessory jack permits you to use Heathkit high voltage and RF accessory probes. Alright, so we've got that. We've got a fold-out diagram with a parts pictorial. And they have a special call-out here for the batteries. It can use a C-cell flashlight battery, and then it needs an 8.4 volt mercury battery, a 1611. And then they give several suggestions on brands of batteries and their part numbers. There's also pictorials for assembling and doing preliminary wiring of the parts on the aluminum chassis. You start with the rotary switch pre-wiring, and there's some nice diagrams for that. And then we get into the circuit board. More wiring from the rotary switch to the circuit board in several stages. Addition of some capacitors, the jack for the accessories, mounting switches, mounting test lead strain reliefs, mounting the meter movement and the front panel potentiometers, making up the test leads, doing some additional wiring. And here we have another fold out with more details on chassis to PCB wiring. And then diagrams for use of the meter and final wiring. Final chassis assembly, putting on the knob. Then we get into the calibration section, which is pretty short, only about a page actually, if you don't count the page turn and the 2 diagrams of the meters. So pretty straightforward. And they have an ohms adjustment section, but there is no ohms adjustment. They basically just tell you how to use the ohms mode. Then there's a diagram showing how you're supposed to snap the aluminum chassis into the outer case. And they have a voltmeter use chart and some meter pictorials. Then a nice section on operation, how to use the test leads, which ones to use for which. The black test lead with the alligator clip is the common or negative lead. The gray shielded lead with the black probe is used to measure DC voltages only. The red test lead with red probe is used to measure both AC voltage and resistance. And then how to make measurements in general, how to do resistance measurements, DC voltage readings, voltmeter voltmeter characteristics, AC voltage readings, AC voltage measurements, and they talk about how it's an average reading meter, not a true RMS meter. So they say it'll give you an accurate voltage if you've got a sine wave, but if you're giving it some other kind of waveform or a square wave or something, you're not going to get accurate readings, depending how much distortion there is from a sine wave. And a little bit about maintenance, talking about replacing the battery, if you happen to build up an electrostatic charge on the plastic cover of the meter, how to deal with that. Talks about the accessory probes. Then there's the in case of difficulty section, troubleshooting in other words. Not too much to it, it's a pretty simple circuit. The usual troubleshooting chart. Specifications, 1 page of them. When measuring DC volts, it has an 11 megohm input impedance on all ranges. When you're measuring AC volts, it's only 1 megohm on all ranges. Its transistor diode complement includes 1 FET or field effect transistor, 4 NPN silicon transistors. Those are bipolar transistors, type 2N3393, which are the same exact, it's the same FET and the same transistors used on the IM-16 and the IM-25 I was talking about earlier, and I'll remind you which I have separate YouTube videos on. Total weight 2.5 pounds. Then there's the circuit description section. And the old habit that Heathkit kicked after doing it for a while, the functional parts list, going through all the components and telling you what it does in the circuit. Then you've got a photograph of the circuit board and the chassis, and circuit board x-ray views, and a voltage chart. On this they actually put voltages at test point locations right on the foil pattern. And then a replacement parts price list if you were to order them from Heathkit. And then the schematic diagram. And finally a couple pages of applications, using it for continuity testing, automobile tests, and so on. So let's give the schematic a look over and talk about the theory of operation a little bit. So I'm going to start out with the actual meter driver circuit. This has a front end that's comprised of an FET in a source follower mode. So essentially whatever voltage is applied to the gate will be also appearing at the source, except this will be very high impedance here. This will be quite a low impedance signal. The source voltage is dropped across this 22K resistor, which goes back to the B- power rail. And just a word about the way this whole family of meters works. I went into more detail on this in my circuit theory on the IM-16 and IM-25, but essentially the meter circuit is a kind of like a difference amplifier, and it's working also kind of as a bridge where you apply a fixed voltage on one side of it and a variable voltage on the other side, and if those two voltages match, then the meter part of it's balanced and it has no current going through it and it has no deflection. But if you have a higher voltage on this side compared to the fixed voltage at this side, then you'll start getting more current flowing from this side to this side of the meter circuit, which causes the meter to deflect upscale. If you had a lower voltage here than the fixed voltage here, then the meter would try to do the opposite. The current would be going this way, the meter would try to deflect downscale, but it can't go much lower than 0. So that's not terribly useful. So the idea here is to always keep the meter biased, or the meter circuit biased, such when you have a 0 volt or 0 ohm, whatever you're measuring out here in the front of the meter, that you end up applying a signal to the FET such that the source voltage is 5 volts, because that matches the fixed voltage of 5 volts on this side. Therefore, there would be no voltage difference between here and here. Therefore, there's no current flowing through the meter. Therefore, it shows 0. Full left-hand position on the meter scale, which is 0. Then if you start raising the voltage out here because of higher voltage or higher resistance, then you have a higher voltage on the gate, you have a higher voltage on the source. This is now higher than 5 volts because that's higher than the fixed 5 volts here. Now you start getting a positive current and a positive meter deflection. So this circuit here requires a low impedance, and this circuit here requires a high impedance, and that's primarily what the FET is doing. It's converting impedances from one side, the upfront scaling circuit, and the sort of downstream meter driver circuit. Okay, with that in mind, we have these two transistors here that normally are trying to operate in a balanced configuration. So the current through this one is the same as the current through this one. They both have 10K resistors on the bottom on their emitter side. So a current going through here across this 10K resistor to B minus, and a current through this transistor down through this 10K resistor to B minus. If you have the same current on both transistors, going through both transistors, then you'll have the same voltage developed across both of these resistors. And like I said before, when you have the same voltage here as you have here, then there's no voltage difference, therefore there's no current going to flow one way or the other through this circuit, which is the actual meter circuit. So it's a balanced bridge, and this does away with some things that the higher end meter, for example, the IM-25 has. It is really the same circuit, the same exact FET, the same transistors here, but they add a common regulated current return so that these are truly constant current circuits and therefore less drifty in theory and more stable, etc. On the IM-16, it did away with that regulated constant or common return between the two sides of the bridge. It just left them up to the battery voltage and drifty parts with temperature and so on. It's just less stable, less accurate. Still works though. And then the IM-25 also had a dual stage amplifier here, so there was two transistors doing this job and two transistors doing this job. On both the IM-16 and this IM-17, the job was done with one transistor on both sides. Again, it's not as good, but it still works. So what do you have here in between these two rails that should be the same voltage if you're getting a 0 reading? Oh, I should say that the B+, the power rail up here that's positive, and the power rail down here that I'm calling B-, and I'm calling it that because on the IM-16 and the IM-25 they actually label it B+ and B-, and it's really the same circuit, so I'm going with that nomenclature here. You don't have the fancy power supply on here, it's just an 8.4 volt mercury cell or mercury battery, and so you should have 8.4 volts from here to here. The functionality of this circuit doesn't care too much what the battery voltage is if you look at it in a simplified fashion, but because there's no constant current source and so on here, it becomes more important that the mercury cell hold its voltage, which is why this guy is not just a couple of alkaline batteries or something adding up to, which is what they did on the IM-16 and the IM-25. They just had a bunch of like C cells providing that voltage, but it could be, it was regulated because of other things in the circuit that were left out here. So that's why this needs to be a mercury cell, because one of the characteristics of a mercury cell is that its voltage remains very constant. It can be used as a voltage reference, which is exactly what's being done here. Once you simplify this circuit down as much as Heathkit did, coming down from the IM-25, then to the 16, then to the 17, you can no longer get along with sloppy voltage regulation on the power supply for the meter circuit. So that's why they threw the mercury cell at it. Now I dare say this circuit will work adequately if you're kind of in the ballpark of 8.4 volts, but you don't want to be too far away from that, or it's gonna, something will get out of tolerance or out of balance or something, and it'll stop working. Now here's another thing about this I should mention before I go much further, is that I said earlier that when you have 5 volts here to balance 5 volts here, that would give you a 0 reading, and that implies that you could go lower than 5 volts here and thereby get a negative reading, and that only works if the overall circuit is set up so that's possible, and it is possible because of this bias circuit here. It's basically a potentiometer between B plus and B minus, but it adds some outrigger potentiometers to allow you to adjust it. And this is the center potentiometer is the zero control on the front panel of the meter. And the objective is to crank this guy up and down until you do get a reading of 0 on the meter when there's nothing connected out here. So any component tolerances or battery voltage differences can be dialed out by this, and you try to get it so the meter reads 0 when you have 0 volts applied out here, or if you're in ohms mode, 0 ohms connected. And what that essentially does is it picks a point halfway between the power supply rails, between B plus and B minus, and halfway between well, halfway of 8.4 volts is 4.2 volts. So really the perfect balance point, if this 0 pot is centered, would actually not be 5 volts, it would be 4.2 volts. But because this can be adjusted with the bias adjustment, you can get it so you end up with 5 volts instead of 4.2 volts, and it still does the same trick. Now, how does the meter actually get current to it or through it when you have an imbalance from this side of the meter driver to this side? Well, if you're in a DC range, and again this is the function selector switch here, and it's shown in the 1 volt DC range, so these 4 here and these 4 here are DC volts, and then the next 4, and also these 4, is AC. And then finally the bottom is ohms. So when the meter is selected to DC volts, then you've got voltage here and it's trying to drive current through a 10K resistor and then through the DC plus and minus switch, and then down through here, through one of these DC positions on the function switch, down here through the meter movement, back out of the meter movement, come up here, go through one of these positions on the function switch, back through this DC plus and minus switch, and to the right-hand rail of the meter driver. So that's the path, and by adjusting this 10K DC cal pot, you can adjust exactly how much meter deflection you get for a given voltage difference, and that allows you to calibrate the DC volts. Similar for AC volts, if you're in one of these four positions, then the path is through this 10K pot, through this, go through all this stuff, back out through these, and to the right-hand side. So same exact circuit, but a different calibration pot when you're in one of those four positions. And then finally, this is not a calibration pot in this case, it's actually the front panel ohms adjust potentiometer. When you're in the ohms position, it's exactly the same thing, except here we have a 15K pot to get from the left-hand side of the meter driver through the switch, through the meter, back out, through the switch, and to the right-hand side. Now you also see here something which I don't think it was on the IM-17 and the IM-25, if my memory serves correctly. This also has a gang off of the on-off switch, and when the meter's in the off position, it shorts out the meter movement. And that's because this is a portable meter that you're going to be carrying around and banging around, and to protect the meter movement from its, if you bang it down hard enough, that very thin wispy pointer on the meter could slam one way or the other and get bent. So by actually shorting out the meter movement through this gang of the power switch, that puts a damper on the meter, an electrical damper, and that makes it so when it does move around due to rough handling, it moves more sluggishly and slowly, and therefore it should not slam into the stop at the left or right hand side of the meter movement and damage itself. And I also mentioned the DC plus and minus switch. All it does is it flops the polarity of this part of the circuit, so that if you've got a DC voltage hooked up which is the wrong polarity, you can, instead of swapping the leads to get the meter to read correctly, you can just move this switch to the other position, and it'll take care of that electronically here. Now you may be scratching your head and saying, wait a minute, how does this, way over in this part of the circuit, compensate for test leads way over here being connected with the wrong polarity? Well, everything in this part of the circuit works just fine with the polarity one way or the other. It has to, because it can accommodate AC voltages. If you have a DC voltage applied up here, then everything here has got the opposite polarity. But remember that the minus lead of the input, in other words, the circuit 0 on the input, comes to this potentiometer here, which is adjusted to be halfway between the power supply of the meter circuit. Therefore, it can go 0 in relation to this circuit. So if you applied, say, a negative, 10 volts out here, this voltage would indeed start going lower than 5 volts. Remember I said it should be 5 volts if you want a reading of 0, but if you have less than that, if it starts going negative over here, this will still work fine, but the FET can't go negative, but its whole circuit is set up to be kind of like a plus 4.2 volts and a minus 4.2 volts because of this. Therefore, it can keep going towards 0 volts, which from the perspective of this circuit is negative voltage. And that will indeed try to drive the meter movement left of the 0 position, But when that happens, you can throw this switch, and now it flops it, so even though the rest of the circuit thinks it's producing a negative meter drive, because of the swapping of the leads here, it can turn it into a positive meter movement. Let's look at the front end of the circuit, and let's start with DC volts. The DC probe has a 1 meg ohm resistor built into it, and if you connect the accessory probe, either the high voltage one or the RF one, it's designed to act like this probe as far as the rest of the meter is concerned. So it's just wired in parallel. So you come over here with your DC voltage, and it's applied to, well, it goes right across here, and it's applied to this big range switch here. And depending which position it's on, let's take a look at the way I've got it marked up here. There's only 4 ranges for DC volts. The 1 volt range, the 10 volt range, 100 volt range, and 1000 volt range. So it's going to be one of these 4. And if you have it set to the 1 volt range, your input voltage is applied again through here and down here. And I'll mark it again. This is DC, and this is AC. So you come through one of these 4. These are all tied together at this stage, and now the voltage is applied to the top of this big voltage divider, which has 5 resistors in it. And then again, if we're in DC here, I'll just mark this everywhere. Okay, so again, the bottom of the resistor divider, if you're in any of the DC ranges, they're all tied together, and it just comes down here and goes through a 10 ohm resistor and back to common. So we have essentially a 6 resistor voltage divider with 9 megs. A tenth of that is 900K, a tenth of that is 90K, a tenth of that is 9K, a tenth of that is 990 ohms. It's going to be in conjunction with this 10 ohm resistor down here. So the 10 ohms plus this actually makes 1000 ohms. And you don't want this one to be 900 ohms. If you do the math on the voltage divider, you need the bottom one to be 1K, which is what you get with the 990 plus the 10 down here. So if you're again reading a fairly low voltage, that voltage is applied across all of the resistors, and now you tap off right here on the top. Here's the 1 volt position. So you tap off right at the top. So if you had 1 volt applied to the probe, you'd get 1 volt right through here and on to the rest of the meter circuit. But if you applied, say, 10 volts out here, and if you put this in the 10 volt position, now it's going to read it from this point in the voltage divider. And if you do the math, you've got 9 megs up here, and then you've got 900K, 90K, blah, 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 blah. All of those add up all the way down. They add up to 1 meg. So it's a 9 meg over a 1 meg, which is a 10 to 1, or a 10 to 1 divider, or a 1/10 divider if you want to look at it that way. So you get 1/10 of the voltage, and if it was 10 volts here on the input, at this point in the divider you'll have 1 volt. So that gets passed through, and once again it seems like it's been knocked down to 1 volt. Same thing happens if you apply 100 volts, but you're on this range. Now you're 1/10 of the way, another order of magnitude down on the divider, so you still only get 1 volt out here, etc. So that's how the input attenuation works. And then those voltages, after they've been conditioned here, pass through this 3.3 meg resistor, which is a current limiter, because if you have too high of a voltage, it needs to be clamped so it doesn't damage all this stuff over here. So that's what these two bipolar transistors are doing. With their bases disconnected, they act like diodes in this case. I got a phone call in the middle of explaining this circuit. I don't remember where I left off, so I'll recap. When you have these transistors, this type of transistor connected like this, they act like diodes. So it's sort of a poor man's diode. I'm not really sure why Heathkit didn't just use diodes there. Well, I think I do. Because a regular diode would have a different voltage threshold before it starts conducting than transistors connected in this way. So this probably works better in this application. Essentially they act as clamps. Interestingly enough here though, this is the thing that's sort of surprising to me. It's showing it's showing an error. It correctly notes that they should be opposite polarities, but they show the emitter here and the collector here, but they show schematically the emitter here. So that is a boo-boo. It should be like that. So yeah, when you have back-to-back bipolar transistors like that, they kind of act like diodes and kind of act like Zener diodes. So they have a different characteristic than just a plain diode in this arrangement. If you think about what's inside a diode like, or a transistor like that, it's kind of like this. With one of these being the emitter, one being the collector, and then the base being here. The base is disconnected, so you basically just have two diodes facing in opposite directions, but they're not identical types of diodes. Yeah, they're both diodes, but they're built differently inside the transistors, so they have different characteristics going one way versus the other. So one of these has to break down and the other one conducts, and it works better in one direction than the other. So that's why they have one of these set up with the emitter up and the other one set up with the emitter down. So they're essentially acting like Zener diodes in this circuit, to put it in a nutshell. If you get too much of a voltage up here, after all the scaling over here, then one of these transistors will start conducting, and it'll act like a short circuit between here and meter common. And that will keep the voltage here from getting too high and doing some damage. And any excess voltage will be dropped across this 3.3 mega ohm resistor. So that's where the voltage, the overly high voltage will be dropped across this resistor instead of being applied to this. And because it's a fairly high value resistor, it keeps the current very low, and therefore these little low power transistors don't actually get fried when that happens. Let's look at what happens when you're in AC volts mode. Well, I'm going to do the same thing I did before. These guys are DC, these guys are AC, and these guys are ohms. And likewise, these guys are DC, AC, and that seems really weird. I wonder why they did that. This is ohms. It doesn't seem like they should have those two wires there. Anyway, so let's look at what happens here with the AC now. The switch is now in the position where these four are tied together, and the signal's coming in from the AC probe, the one that does not have a 1 mega ohm resistor in it. So it goes straight through here. Immediately it has a series capacitor, and that blocks any DC component. So if you've got, for example, an AC signal riding on a DC signal, the DC part is stripped out by this capacitor, and all you're going to measure is the AC part, because that's all that can get through the capacitor. and then that is dropped across a 1.8 mega ohm resistor in series with a 200K resistor. And if you think about what's 200K, right? Well, it's 0.2 mega ohms. So these two together end up being a 2 mega ohm resistor. And then back to ground. So it's a voltage divider. But for the lowest ranges, the 1, the 10, and the 100 AC volts ranges, the signal just comes straight through here, one of these three, and then goes through this diode, gets rectified, and then goes on its way. But if you're in the 1000 volt range, I believe that's the correct, that should be 1000 volts in that direction. Yeah, I think it is. Then all of a sudden this voltage divider comes into play, where you get a fraction of the voltage dropped across this 200K resistor, and that's what passes through the switch. So you add some attenuation up here when you're in the highest voltage range on the function switch. Otherwise the voltage passes through on the three lower ranges. And then you've got a capacitor to ground. I'm presuming that's there to shunt some higher frequencies away, so it's responding more to the lower frequencies. Then you go through a 33 mega ohm resistor, and it doesn't matter which of the four AC ranges you're in, it just goes straight through, and it's applied to the top of this same voltage divider you had for DC volts. And indeed, it comes out the bottom just the same way as DC volts. Let's look at what happens over here. If you're in the lowest range is not 1 volt, it's 1.2 volts. And that comes right off the top of the divider. The 10 volt comes off of the same place it does for 10 volts on DC. The 100 volts comes off the same place it did for that. And the 1000 volts, however, does not. For DC volts, we're tapping off this point in the divider, but for AC volts, we're tapping off 1 point higher up. Yeah, so both 100 volts and 1000 volts are treated the same when you're dealing with AC volts, so that's tapping off the same point in this resistor divider, but that's compensated for by when you're in the 1000 volt range over here, you get some additional attenuation. And I think that's largely a trick that Heathkit's using to avoid having too much voltage applied to this diode. It's not rated for the highest voltage you can apply to this meter. So when you are in the 1000 volt range, it knocks it down before it's applied to the diode, then it gets rectified, then it's compensated for here, the fact that you had some attenuation here, it's compensated for by playing a game with the range switch and which part of the divider you're tapping off of here. And you'll notice that on the actual meter, there is different ranges for AC volts on the meter face. Different scales, I should say. They're color-coded, black or red, and the scales are a little different. And that is largely because of this kind of game that we're playing. It deals partially with the significance of the voltage drop. It's pretty insignificant when you're on a higher voltage range, but when you're on a lower voltage range, that voltage drop through this rectifier diode becomes more significant, so they skew the meter scale to compensate for that. And let's see, yeah, everything else is exactly the same as with DC volts. Now let's look at ohms. Now ohms was very funky on the IM-16 and IM-25, and I was at some pains to describe how that worked in my videos on those meters. But it's much simpler on the IM-17. It's so simple that you almost wonder why it would work adequately. And I should note that the basic ohms reading function is done with this circuit right here, this little loop. So, and this circuit is made whenever the power switch is in the on position. It's not on position and in ohms function. It's just anytime the meter is turned on, you've got, well, I'll take that back. One would think that you would want to have this circuit here active only when your power is on and you're in ohms, and that's what happens here because the battery is in series with the power switch, which is in series with the 4 positions of the range or function switch. So this battery does not get depleted if you're measuring AC or DC volts. So let's look at what happens here. This battery here provides the excitation voltage for the ohm meter circuit. And that excitation voltage is needed because when you're measuring resistance with a multimeter, or any kind of meter really, that I can think of off the top of my head, you ultimately are trying to put some current through a resistor under test. And then because the resistance is proportional to the voltage drop, assuming the current is staying more or less the same, then you just measure the voltage drop across the resistor under test. So here's the meter circuit redrawn to be maybe a little easier to understand. So once again, I have the 1.5 volt C cell here, and then it produces current that goes all the way through all these resistors here, but it depends upon what the range is. So if you've got the range set to the R times 1, in other words, whatever it shows on the meter scale is the actual resistance. So let's say it's in that position like I've shown the switch. Now the current just goes through here, through the test leads through the resistance under test and back to here. So you have this current flowing like this. And this resistor here is, for all intents and purposes, a 10 ohm resistor. Now, that's with nothing connected out here. What if we put a 10 ohm resistor here? Let's say this guy is 10 ohms. Well, let's simplify that a little bit more. Let's say that this resistor here is 0 ohms. It's a short circuit. So we still have the battery, we still have this nearly 10 ohm resistor, and then a short circuit back through here to here. So we have a voltage drop across this nearly 10 ohm resistor due to the fact there's current going through it, and since it's the only resistance in the circuit, it's going to be dropping the full 1.5 volts that the battery can produce. Well, this point here is also tapped off of and sent through this resistor to the FET, where it's presented to the meter movement. Well, the way it works out on here, combined with where the bottom of this circuit is tied into the meter driver circuit between B plus and B minus, it works out that that situation there will give you a reading of 0 on the meter, just like you would expect with 0 ohms. Now let's say we put a 10 ohm resistor out here. So with 10 ohms here, and this still in the times 1 position, essentially what you're doing is putting a 10 ohm resistor out here. So now the circuit is just this. Well, that's nearly the same thing as this. So now the voltage provided by the battery is dropped almost equally by this resistor and by the 10 ohm resistor up here. So you get half the voltage, and that would you'd think that would give you a meter reading of half of scale, right? Well, it turns out that right about smack dab in the middle of the meter scale is the number 10. So this meter is set up as a 10 ohm center nonlinear meter display. Now let's see what happens if you put a larger resistor out here. Now you have to change the range here, and now you're introducing more resistance here. It's not just 10 ohms anymore. Now it's 9.1 plus 9, or whatever this guy is, 990. I didn't write that in. 990 ohms. Now you'd have 990 plus 10, so basically 1000 ohms here, and then whatever resistor you've got out here. So now let's say you put a 100 ohm resistor out here. Now it's a 100 ohm resistor, or I'm sorry, it goes up in 2 orders of magnitude. Let's say we put a 1000 ohm resistor out here. Now it's essentially in parallel with the 1000 ohm resistor made out of here. So once again, we would get about half the voltage of the battery out here, and it would still give you a mid-range reading on the meter, which is 10 on the scale, but we're now in the times 100 position here, right? So 10 times 100 is 1000, and that's what we would have out here if we had a 1K resistor. And the same thing happens going up and up and up. So the way the IM-16 and IM-25 worked, which I've described in some length, is that it actually produces a constant current and then dumps it across I think it's a 10 ohm resistor, which is the bottom resistor in the current or the voltage divider, and then it places the resistor under test across that 10 ohm resistor, so they're in parallel. And I was starting to describe it that way for this until I realized that's not exactly what Heathkit did with the IM-17. The resistor under test is put in parallel with the combination of the 1.5 volt cell and the 9.1 ohm resistor. It's not in parallel with just the resistor. So that changes what the circuit's doing. Here's a simplified way of looking at it. Let's say we've got it in the times 1 range. So you've got the 9.1 ohm resistor, the battery, and then say a 10 ohm resistor out here has the resistor under test. And it just makes this simple little circuit. So the 1.5 volt battery is trying to drive current through these two resistors and back to itself. And the voltage from here to here is what's being measured by the voltage out there. Well, what good does that do us? Well, if you pretend like this stuff isn't there, the meter circuit downstream is actually measuring the voltage across the resistor under test, is what it's doing. Let's redraw that. The positive side of the battery is up here, like a 0.15 volt power rail. Then we've got the 9.1 ohm resistor here coming down. Then we have the resistor under test, and then back to the minus side of the battery, like a 0 volt ground in the circuit. So now, instead of being two resistors in parallel, we're looking at it as two resistors in series. And the meter downstream is always measuring the voltage across the resistor under test, instead of like it did on the other meters where it's measuring the voltage developed across this resistor and this resistor in parallel. Here it's just doing a voltage divider. So let's take, for example, let's say that we do have a 10 ohm resistor here. If we do the Ohm's law to this, you'll end up with 0.785 volts presented to the rest of the meter. And that's assuming that you've got a 10 ohm resistor under test. And let's see if we double that and made it a 20 ohm, you do the math, you end up with 1.03 volts. So it's a higher voltage being developed for a higher resistance, and so on. But you can see 20 ohms is double 10 ohms, but you don't get double of 0.785 volts. So already we've got a nonlinear response, which is why the scale on the meter in the ohms mode is very nonlinear. It has to take into account this kind of response. And then again, the only thing we're doing when we're going to a higher range, instead of R times 1, for example, is we're making this resistor here bigger. So a larger part of the upper part of the resistor divider is larger, and you still crank through Ohm's law and you still get the same thing. In the times 1 mode, a 10 ohm resistor will give you a mid-scale reading, because that's where the scale is calibrated for a reading of 10. If you are in the times 100 range, then this resistor here gets another resistor added to it by the range switch, and it ends up being just a little bit under 1 kilo ohm. So now you've got, if you put a 1K resistor down here instead of a 10 ohm, now you'd once again have a similar relationship between this and this, and you'd still get half the battery voltage, 0.785 volts, which would drive the meter to a reading of 10 on the meter, but now you're in a times 10 range, or times 100 range, so 10 times 100 gives you 1000, and that would be the value of the resistor. And the same thing happens. You just keep going up by an order of a couple orders of magnitude for the 4 ranges, and that always ends up putting you in an appropriate part of the meter scale. Okay, here's the chassis of the other IM-17. You can see that there's still a 9-volt battery in the old mercury battery clip, but it's using the original clip, and the battery's just sort of jammed in sideways. And it also uses just a 9-volt battery connector on wires instead of on a clip on the battery holder. And thirdly, there are no series diodes on this 9-volt battery. And here's a rear view of that same chassis. It looks just like the other one. Here's the black plastic case, and although this picture shows it after I made the repairs, the whole right side or lower right side of the case was cracked all the way through from top to bottom, and also the right front corner on the bottom part of the case was cracked at the corner, rendering the case unserviceable. Here's a view of the inside of the lower right side of the case. You can see 2 crudely painted aluminum sheet metal plates, one right up against the right corner and a wider one to the left. There's 2 plates there because I had to preserve the groove in the case into which the meter chassis fits. The 2 aluminum plates are epoxied to the plastic, and unfortunately I was in a rush to get this done, so I tried painting it before the epoxy was cured. The reason the paint looks so crappy on there is because I shot it while the epoxy was still not completely cured, and there's a reaction between the uncured epoxy and the paint. This is an external view of the same area. I put a bunch of 440 button head screws
through holes drilled in the plastic and then tapped into the aluminum plates on the inside. And that's necessary because if this case flexed without those screws being there, it would just break where the epoxy is bonded to the plastic and it wouldn't hold up. With the screws and the epoxy, it's pretty strong, just a little ugly. Looks like Frankenstein's monster. Here's what the case looks like with the meter chassis snapped into it. Because the meter chassis design did not change in its dimensions between the first version and the second version, it does fit into the case just fine. Here's the finished product with the case repair complete and the meter in it and fully functional. And here is closing the case. The case closed just fine, but the only thing that originally held the case closed was fine alignment on the handle, top and bottom halves of the handle. They would snap together in a way that would hold the entire case closed. It's a rather poor design. If there's any distortion whatsoever on the top or the bottom of the case just due to age, wear and tear, whatever, then the two halves of the handle don't match precisely and the latching function doesn't work. So I couldn't keep the case closed. It would close, but it would just spring back to this position as shown. I didn't see a real good way of rigging that up. The magnet fix wouldn't work because there wasn't really enough space to put any meaningful magnets on this. And I had decided to donate this to the Vintage Computer Festival Midwest, and I needed something to hold it shut, so I just used a little strip of double-sided Velcro to wrap around the handle, and that held it shut. A bit of a kludge, but it's a donation, and my understanding was they did sell it at auction and raised a few bucks to defray the cost of putting on the computer festival.